usually when the bell rings, actually 15 minutes. But it also depends on your schedule. You might want to.
So we have until 3, and then I have from 3:15 until 4.
But basically, Onur wants you to finish your slide. So
yes.
I think that's.
So what if I want to take 5 minutes after 4? Is this possible or impossible? Like what's the flexibility?
5 minutes. You can tell them that. But this. Okay. Just tell them that. Okay. So hello, everyone. Before we can start with the lecture of today, I'd like to make an announcement. I think you have already received our survey to review the course, Digital Design Computer Architecture. This has been started, I guess, yesterday, if I'm not mistaken. Basically, we'd like to encourage you all to attend to this survey and provide constructive feedback. Professor Mutlu and I, we are very, very much open to receive all your feedback and basically improve the course for future editions of this. So please make sure you attend it. I think the survey will stay open until June 2nd, but would be good if you can do it as soon as possible such that you don't forget it. So with that, I will stop and then Konstantinos will take over. Thank you.
Hi, everyone. Thanks for joining today. So I'm going to deliver the lecture on my favorite topic, which is virtual memory. Okay, so who am I? I'm a 5th-year PhD student working in Safari Research Group. I did my bachelor's and master's at the National Technical University of Athens. I come from Greece. And my research interests lie in hardware and OS co-design with a focus on virtual memory and memory management. Also hardware-software co-design with a focus on programmability and intelligent interfaces. And I'm currently also working on security primitives for emerging and futuristic systems. I would encourage you to read this blueprint written from Onur on intelligent architectures for intelligent computing systems, where Onur tries to give an understanding of how we should design fundamentally better architectures at whose core they should be data-centric, data-driven, and data-aware. And as I will explain today, being data-centric, data-driven, and data-aware requires a very strong virtual memory subsystem so that we can support these functionalities. I would recommend these readings for you so that you can understand and dive deeper into the topic. These are from the book, and this is also from 3 publications from our group, which can do you can read a very concise background on the topic. So let's dive into virtual memory. So as you have seen right now in the course, we have a memory and a programmer. So how things work is the following. When you write your Python code, let's say, you want to load from memory some stuff, store to memory some stuff, and this is your interface that right now you're using to program. Ideally, we would like a 0 access time latency, which means we go to the memory for free, we return from the memory for free, we take our data for free. Second, we want the memory with infinite capacity. Imagine what would happen if right now you had a 1 terabyte memory in your MacBook Pros, and you could run, let's say, the Llama or the OpenAI stuff locally on your device instead of waiting for the network and the congestion in the network. Third, zero cost. We don't want to pay anything for our DRAM, for our main memory. And fourth, infinite bandwidth. With infinite bandwidth, we want to basically support multiple accesses in parallel to the main memory. So what is the abstractions we're going to talk today about? So the programmer, when you write a program, you do not see the physical memory. You only see virtual memory. This way, you can assume that the memory is infinite. When you write in your Python code that you want to allocate a dictionary, you want to allocate a NumPy array, then that doesn't mean that you see the actual physical address that you access in the system. You don't, actually. You see a virtual address, which is an abstraction. Why does this happen? Because in reality, the physical memory might be much smaller than what you assume when you write your program. You don't want to care about what is the physical memory in your system. So the system tries to hide this information from you using both software and hardware, and cooperatively, it tries to map virtual memory addresses to physical memory. So you as a programmer do not need to do anything. The system automatically manages the physical memory transparently from the programmer. So the programmer does not need to know the size of the physical memory or manage it. So you can have a small physical memory, which appears to be very huge from the programmer's point of view, and you make the life easier. Imagine what would happen if you would need to rewrite your program for every different physical device that lies in your system. Then you would not basically, you would lose the portability argument. You would not port your program from your laptop to your desktop to your cloud environment. However, adding this support in the systems makes the system a lot more complex, both in terms of the software stack and as well as the low-level stack, the hardware stack. This is a classic example of the programmer microarchitecture trade-off. So we offload in this concept of virtual memory the burden down to the system organizer and the architect, and we remove the burden from the programmer so that we can increase productivity on the programmer's side. The question is, why do we need virtual memory? And there are many benefits of automatically managing memory. So programmer does not need to deal with physical addresses first. Each process, when you write a process, it has its own physical address, virtual address space, and it has an independent mapping from virtual to physical addresses. So when you write your program, your NumPy array, let's say in Python, or your C array, which you allocate using a malloc, then this is represented using virtual addresses, which is an abstraction. So somehow each process needs to keep track of the virtual addresses that correspond to this array and how they map to the actual physical device where you store your data. And this enables, first, code and data to be located anywhere in the physical memory. And given this, we can relocate and flexibly locate our data. Imagine if you would write your program and you would only place the data in a specific physical location, then you would not be able to relocate the data from one to another. Second, we can isolate and separate code and data of different processes in physical memory. Imagine if you want to share your computer with a friend of yours, and you both want to write your programs. Then you need a consensus about who is going to use the physical resources. However, with virtual memory, you don't need this consensus. The system does it for you. Third, code and data sharing between multiple processes. Again, you co-op coding with your friend, you write two programs, and then you do not need to basically agree upon the physical locations you're going to share. The system can do it transparently for you using virtual addresses. And we can share basically code and data this way. This is an example of a system, a very old system. This was used in most early supercomputers, in early personal computers, and many older embedded systems, where we would have a CPU, and on the back end we have a memory, a physical memory device, and the CPU uses loads and store instructions that generate physical memory addresses. We don't have the concept of virtual memory in this scenario. And let's see what are the downsides of this approach. So first, physical memory is of limited size. So what happens if my program needs more memory than the size of the physical memory? So for example, should the programmer be concerned about the size of the code and the data, whether it fits in the memory, where should I place it in the memory? Should I, for example, should the programmer care about whether the data is fetched from the disk, whether it's fetched from the memory. Should the programmer care about fetching it from the disk to the memory or back and forth? Next, multiple programs may need the physical memory. So if multiple programs need the physical memory and they're concurrently running in the system, right? So should the programmer make sure that all the processes can fit in the physical memory? What if I write a code that simply allocates the whole memory, does not leave space for anyone else? So should also the programmer ensure that two processes do not unintentionally or incorrectly use the same physical portion? If you would decide on where to place your data in the physical memory, you would again need a consensus with all the other programmers that write programs in that computer about where to place your data so that you don't overwrite each other or that you don't read the data of each other, which creates both security problems, synchronization problems. Also, as you have seen in the course, we're using instruction set architectures which have an address space which is much larger than the physical memory size. So for example, we use a 64-bit address space with a byte addressability that can cover up to 16 exabytes of data. So what if you do not have enough physical memory to cover up the 64-bit address space? So the difficulties of the direct physical addressing are the following. So we have a programmer which needs to manage the physical memory space. Again, we repeat, it's inconvenient and difficult. So it's more difficult even when we have multiple processes in the system because they need to coordinate with each other. It's also very hard to support code and data relocation. Why? Because addresses are directly specified in the program. We cannot change the location of these addresses once you write your program. It's also difficult to support multiple processes running concurrently. Why? Because we cannot guarantee protection and isolation between the multiple processes. We cannot guarantee that 2, 3, 4 entities that write programs in one single computer have the consensus that have agreed that they're going to use different parts of the physical memory for their programs. This would create problems basically with sharing physical memory. And it's also very hard to share data and code because, again, we need some synchronization between the entities that use the same computer need to agree on which data and which code they're going to share. So the question is, okay, we agree that using the physical addresses directly is a problem. Does anyone have any question on that? No. Okay. So let's see right now how to solve this problem, which is how does virtual memory work? So the idea here is that we give its program the illusion of a very large address space, even though we have a very small physical memory. This way, the programmer does not need to worry about managing the physical memory. In this scenario, the programmer assumes that they have an infinite amount of physical memory, and underneath, the hardware and the system, the operating system, cooperatively and automatically manage the physical memory space to provide the illusion that it's maintained for its independent process. But we need some sort of indirection. And why do we need that? Because when the program generates an address in this scenario, when you write your programs and you generate an address, you basically express your data structures using virtual addresses. But we cannot use right now the virtual address to access the actual physical device because we do not know the physical location of the data based on this virtual address. This virtual address is called linear address in the x86 systems, in the older systems. And we need a mechanism which we call address translation that maps the virtual addresses that you use in your programs to physical addresses that correspond to the addresses that lie inside the physical byting storage. This is called the real address in x86. So we have another translation mechanism responsible for dealing with the problem of virtual to physical mappings together in hardware and software. The programmer does not need to care about how this is happening, how this translation is happening. Let's see an example. So we have spawned two applications in the system, and these two applications have a different virtual address space. Application 1 uses virtual address space 1, application 2 uses virtual address space 2. And we have the physical address space. And the physical address space, imagine it as the physical memory. So the first thing that the system does is that it splits up the virtual address space and the physical address space into discrete chunks, which are called pages. So when we want to do a mapping, we will do it between pages. We will not do it with arbitrarily sized segments. In this example, app1 uses 2 pages, and app2 also uses 2 pages. In this example, again, app1 maps these 2 pages on the second and the third physical location in the memory, while application 2 maps it in the fourth and the sixth. This is what we call a virtual to physical address mapping, the process of establishing a mapping from the virtual address space of an application down to the physical memory. But to be able to discover this virtual to physical address mapping, we need some sort of indirection. We cannot directly access the physical memory from the virtual address. We need someone to translate for us. So these are the key 4 issues when it comes to this indirection and mapping. First, when do we map virtual addresses to a physical address? Second, what is the mapping granularity? What is the page size? Like, do we split our virtual address space in 4 kilobytes, 8 kilobytes? How do we make this decision? Third, where and how do we store the virtual to physical mappings? Again, we need some sort of information about where the virtual address maps in the physical address space. So how are we going to find out where is this mapping? And how do we find out where to find this mapping? And fourth, what if we fill up the memory, even though the virtual address space is much larger? We mapped our data through inside the whole physical memory, and we somehow need to deal with this problem. So in modern systems, when do we want to map a virtual address to the physical address? In most modern systems, we do this when it's first referenced by the program. So once the programmer goes and performs a write operation that I want to write to this virtual address, the system underneath tries to prepare the physical location for us so that we can store our data. What is the mapping granularity? In most modern systems, we're using multiple granularities. In your MacBooks, for example, you're using a 16 kilobyte pages. In Ubuntu and Linux, they're using 4 kilobyte pages. They're also using 2 megabyte pages. Where and how do we store the virtual to physical mappings? We have OS system structures. I will discuss this later. They're called the page table, which stores the virtual to physical mapping. We can think of it as a dictionary, basically, where you go with your virtual address and you get back the physical address. And what do we do when we have a full memory? We need to evict some sort of pages, right? And we need to evict some sort of pages to bring the ones that we want to use at that point in time. So let's go to the concept of virtual pages and physical frames. So the virtual address space is divided into pages, and the physical address space is divided into frames. I never understand why there is a distinction between these two, but that's how you can find in the literature. I call them pages, all of them. The virtual page can be mapped to a physical frame if the page is inside the memory, or a location in the disk. So if we access a virtual page that does not reside inside the memory, but is on a disk, then we need to bring the physical frame from the disk inside the physical memory and adjust the mapping. And this is called demand paging. This is called demand paging because we're fetching the data inside the physical memory only when they're accessed. We do not, when you create an array in C with 1 million elements, your system underneath does not reserve 1 million elements for you. Only when you do the writes, when you start writing and initializing this data structure, you start allocating physical memory in your system. And where do we find these mappings? In a data structure called the page table, which is actually, you can think of it as a dictionary. The page table is imagined as a dictionary that stores the mapping between virtual pages to physical frames. In other words, what you have seen in the course, the concept of caching, and physical memory, you can think of it as a cache of pages which are stored in the disk. In fact, basically, it's a fully associative cache in modern systems because we can map a virtual page anywhere in any free physical page in the main memory. And there are similar caching issues which we have covered earlier, like how do we place a page in the cache? What page can we remove to make room in the cache? What is the granularity of the management, like a cache block? How large should be the cache block? And what's the write policy? Do we write directly to the memory? Do we write directly to the disk? How do we handle these? And you can find this analogy in this table. Again, this is the virtual to physical mapping. So on the left, you have some virtual addresses, right? And as you can see, some of these virtual addresses map to the physical memory and physical addresses. However, in this scenario, some virtual addresses do not just map to the physical memory because, for example, it was full, and they map also to the hard drive. So, but we need to guarantee the system that most of the accesses hit in the physical memory. Let's take an example of a virtual memory size of 2 to the power of 31 bytes, which is 2 gigabytes. A physical memory size which is much, much, much smaller than the virtual memory size, which is 2 to the power of 27 bytes. And a page size which is 4 kilobytes, which means that for inside each page, we store 2 to the power of 12 bytes. So what is the organization here? So how many bits do we need for the virtual address? 31. We need 31 because it's a log of 2 to the power of 31. What's the physical address size? We only have 2 to the power of 27 bytes, so we do not need all the 31 bytes for the physical address. We only need 27 bits. And what is the page offset? 12 bits. And we need the page offset to find the location of the data inside the page, basically. If we have a 4 kilobyte page, using 12 bits, we can express where our data is inside these 4 kilobytes. So how many virtual pages do we have? We have 2 to the power of 19 pages. Why? Because we divide the virtual address size, the number of virtual pages, the size of the virtual address space, divided by the number, the size of the physical page, which is 2 to the power of 12, which means that we need 2 to the power of 19 virtual pages in the system. In the case of the physical address space, we have 2 to the power of 27 divided by 2 to the power of 12, as you can see here, and we have 2 to the power of 15 pages in the system. So we need to map the 19 bits for the pages in the virtual address space to 15 bits in the physical address space. So you can see here that our job is the following. So we have 19 bits in the virtual address space, and these 19 bits represent the virtual page number, and we need to always translate these 19 bits to some bits in the physical address space, to 15 bits in the physical address space. As you can see, the page offset remains the same. Why? Because the page offset only tells us where is our data inside the page. We do not need to translate the page offset. We do not need to translate at the granularity of the page offset. Is that clear to everyone? Okay, nice. And the question is, how do we do this translation? So we use a data structure called the page table. And the page table has an entry for each virtual page. And each page table entry has a validity bit. And the validity bit tells us, oh, this virtual page that you're trying to translate is located in the physical memory. It's not in the disk. So using the validity bit, we know that indeed our data is inside the physical memory. We also get the physical page number. So when we probe the page table and we look it up, we need to retrieve back where the virtual page is located in the physical memory. And then typically the page table has some additional bits per entry to know the permissions we have about for the page, some replacement policies, which ones to evict or not. This is an example of the page table. You can see that there are in this scenario 4 entries which are valid. And let's see how we would translate in this scenario. So we have the address 0x0002. So the first thing we do is we take this VPN, this is the virtual page number, which we need to translate, and we look up the page table at the corresponding entry. In this scenario, it's entry number 2, so we start from the beginning of the page table, and we can access the third element, which is 0xFFFF. So in this example, when the programmer wanted to translate, it would take the 0xXXX2, then you would look up the page table, and you would get back the 0x7FFF, which means that after the page table entry is done, then I can form my physical address using the page offset, which remains the same, and the corresponding physical address. However, how do I know where my page table starts? So how do I find the physical address, basically, of this element? there's a concept in almost all the page tables and all the data structures in the system, which is called the base, right? So in this example, the page table is allocated as a contiguous structure in the physical memory. And we always know when we want to translate the beginning location of the page table. That's how we can form the corresponding location here, which is the third entry, and find out the pointer which we need to load, which would contain this, the 0x7FFF. Next example, we have the address 0x5F20. And in this example, sorry. How do we do this? We first form and find the page offset and the virtual page number. How do we do this? We shift by 12, because these are the number of bits for the page offset. And then we take the rest of the bits, which is the 0005. Which entry do we need to look up in this scenario? Because we have the fifth virtual page number, we need to take a look at the sixth entry, 0, 1, 2, 3, 4, 5. The sixth entry of the page table. And in this scenario, again, we find that the physical page that the fifth virtual page corresponds to, it's the first physical page in the physical memory. A next example, a more complicated one. We form again the virtual page number, which is 7, and the page offset, which is the 3E0. And in this example, we need to access which entry is the 8th entry in the page table. So we access the 8th entry, and what do we find out? We found out a 0. Does anyone know what is a 0 in this scenario, based on what we discussed? So we don't find the validity bit. Our data is not in the main memory. Then where is it? That's correct, but that's not what I want to hear as an answer. It might be in the virtual memory and not being initialized. But usually what happens if you want to load a file which has not been brought in the physical memory? Where would the data be? Anyone? So the data would be in the disk. Oh, sorry. The data would be in the disk. Because the data is not in the physical memory. We already have a file with the data. And we figured out in this context, from the page table, that our virtual address has not been mapped anywhere in the physical memory. So we fetch it first from the disk. And the question is the following. Let's say we have a 64-bit virtual address space and a 40-bit physical address space. And the question is, how large should the page table be? So if you have a 40-bit physical address space, how large should the page table be? Does anyone have any idea? Like, how can you need to somehow support translation for each one of the virtual addresses that can be stored in a 64-bit virtual address space. Then how large would the page table be in this scenario if we store it as a contiguous array? Let's say that the page table stores 4 kilobyte pages. Does anyone have any idea? So you would need to address you need to look up every single virtual page number. And in this example, if you have 2 to the power of 52 entries for the virtual address, why do you have 2 to the power of 52? Because you have 64 bits for the virtual address minus the 12 bits for the offset, which do not need to be translated. So you would need to translate 2 to the power of 52 entries, and each pointer, each physical pointer for the physical frame would be 4 bytes. So you would need, in this context, 2 to the power of 54 bytes for the page table. And this is just for one process. If another process using another virtual address space would need a page table, you would need to store another 2 to the power of 54 bytes. Do you think this is feasible? Like, imagine if we would need to store in the physical memory 2 to the power of 54 bytes for each process. I guess no system would be able to run today. So the challenge number one is that the page table is very large, or at least part of it needs to be allocated in the physical memory. And the solution that people have come up to solve this problem is a multi-level hierarchical page table. So let's see how multi-level page tables work. So we need to organize the page table in a hierarchical manner such that only some parts of the page table need to be allocated in the physical memory, so that we don't need to store the entire 2 to the power of 54, let's say, page table in the physical memory. So how does that work? We have, in this example, 2 page tables. We have the first level page table, as you can see here, and the second level page table. So the first level page table, which is much, much smaller, we store it in the physical memory, always, we allocate it. And what do we do then? We split our virtual address into 2 distinct numbers, the page table number and the page table offset. To access the first level of the page table, we're using only 9 bits, which correspond to the page table number. These 9 bits mean that we can access 512 different entries into the first level page table. So the key idea here is the following. If an entry at the first level of the page table is not allocated, then we do not need to store the corresponding entry in the second level of page table. You can see this example here. So we have in the first level of the page table, we have 2 valid entries, the second one and the last one. So what does that mean essentially? We're storing only 2 entries in the first level of the page table. For all the intermediate zeros, we do not need to store a pointer to the next level of the page table because this has not been touched yet, it has not been allocated. So what do we gain from this? That we would store the second level of the page table only for the entries which are valid in the first page table. So if our process is using just this entry to map the data, to map the data to the physical address space, then we would store only 1 frame from the second level inside the physical memory. We would not need to store all the entries that correspond to the first level of the page table. Is that clear to everyone? Yes? You want to ask something? Okay. And that's how modern systems employ the page table. They basically have multiple levels so that each level can basically act like a tree. And as you can see here, they split the virtual address into 4 chunks of 9 bits. And you have a CR3 register, which is used in the x86, 64 systems in your Intel processors. And the CR3 register points to the beginning of the first frame. So once it points to the beginning of the first frame, you're using the first 9 bits to find the offset inside the first frame. If we have a valid bit in the first frame, then only we store the second frame, which basically we use the second 9 bits to find the offset inside the second frame. From the second frame, we find the pointer to the third frame, only if they're allocated. And we do this iteratively 4 times until we find the last frame, which is called the leaf of the page table. You can think of it as a tree data structure, if you have seen linked lists, for example. And after we reach the final level of the page table, that's where we retrieve the physical page number. In this scenario, again, for all the entries inside all of these frames, which are not valid and are not initialized yet, we do not need to store pointers to the next level. So there are no next levels, basically. So we would store only the frames that correspond to the virtual addresses that we're using. If we do not use a large portion of the virtual address space, then the page table becomes smaller and smaller and smaller. So as you can see, how many accesses we would need? How many memory accesses do we need to access the page table in these systems? We need 4 memory accesses, 1 for each level, given that the virtual to physical mapping exists. So in this example, you saw that we need 4 sequential memory accesses to retrieve the physical address during the page table walk in x86 64 systems. So we tried to solve this challenge that the page table is large. And we figured out that the multi-level hierarchical page tables are a good solution towards that. Second, and very important, when we perform an instruction fetch in the system or a load or store, then we need two memory accesses. Right now in your systems, when you access, let's say, the location of an array, let's say A of I, the system does not only perform one memory access, it performs two memory accesses or more. Does anyone know why it performs more than one? Like why would you perform a second memory access even though the only thing you want to access is A of I?
Well, we're accessing a virtual memory address, right? So it has to kind of go and look up into the page table, go and look where the real address is, so they do that access up.
Exactly. So your system somehow needs to perform a second memory access to figure out the contents of the page table, to figure out where it would go to the physical memory and search for your data. So you want one address for the address, one memory access for the address translation or more in the modern systems, and you have one access to the data within the physical address. Once you retrieve the physical address from the page table, then you can access your caches and your physical memory. So we want two memory accesses, which, as you can understand, if for every single virtual memory access I'm doing, I need to do a second one, I'm going to basically degrade performance by almost 100%. And if I have the multi-level page tables, which have, let's say, some sort of pointer chasing, I jump from level to figure out the final level, then I would need to perform more than one memory accesses to find them. Unless we're more clever and we try to speed up the translation process somehow. And everything boils down to how we perform the address translation in modern systems. So to support virtual memory and the address translation process, we require support from both the hardware and the operating system. So the page table is stored inside the memory, and it is the job of the software of the operating system to populate the page table and decide what to replace in the physical memory. We talked about the page table register before. The page table register, given that the page table is a per process structure, needs to change every time we run a different process in the system. We cannot use the same base and pointer to the page table. Third, we need to handle page faults and ensure the correct mapping. I'm going to talk about page faults in a bit. So the next question is, how does the CPU, when it's running, discover this virtual to physical mapping? How is it accessing the page table? So we obtain the physical address from the virtual address using the address translation, and we do this at the granularity of the page size. The page size is specified by the instruction set architecture. Basically, it's a contract. Hardware and software have agreed that they're going to split both the physical page, the physical address space, and the virtual address spaces in 4 kilobyte chunks. So the page table contains an entry for each virtual page. This is called we will call it the page table entry for simplicity. And in a PTE, we basically store the translation and some other memory protection bits. So how does address translation happen? We have a core. Right now, you're using, let's say, your ARM cores in your CPUs, in your laptops. And the core tries to access a memory location using the virtual address. You're using A of I, let's say. And it goes to the memory hierarchy. And the first thing it needs to do is it needs to load the page table and find the page table entry. The page table entry is, let's say, the leaf, the final entry from the page table that contains the translation. So for every virtual address it's doing, for every virtual address it's accessing, it would need to go to the memory hierarchy to find the translation. And the question is, how can we speed up this process that degrades performance a lot? First, let's see some definitions. You can think of the page table as the tag store for the physical memory. So it's a mapping between the virtual to physical memory, and we define PTE as the tag store entry for a virtual page in memory. So we need a validity bit, we discussed this before. We need some tag bits, the physical frame number, and we need support, we need bits for support for replacement, and a dirty bit to support write-back caching. I will discuss this later. So the big question also, before we jump into the translation, is like, who would establish a mapping? Who would update the page table? Who would give us the location of our data in the free physical memory? Again, we have an application here with a virtual address space. And this is the physical memory. You can think of it as a RAM in your systems, right? So when the data is being touched from the virtual address space, which means that the programmer needs to perform a write to this piece of data, we need to find out and somehow establish the location that this data would be stored in the physical memory. So we need to map, essentially, the virtual addresses to the physical addresses. And this process of mapping them is called the fault in the systems. So virtual addresses are not mapped to the physical memory in this example. So someone needs to take over, which is the operating system, that would handle the memory allocation and place the addresses from the virtual address space to the physical memory. How does that happen? When this happens in your system, also in your system nowadays, so the application gets stalled, and the operating system takes over and says, okay, I have this virtual address, and I need to place the data that corresponds to this virtual address somewhere in the physical memory. So my job is to first find free space in the physical memory of where to put my data. This is a simpler scenario that your colleague also said before, which is called a minor fault. The minor faults happen usually when I allocate memory for a very big array. It's not backed up by any file. I simply used as my program just allocates a large array as an intermediate data structure. Data has not been mapped yet to the physical, has not been allocated yet in the physical memory. And somehow we need to handle, the only thing we need to handle is finding the free space in the physical memory. That's the only thing the OS needs to do. This is the good scenario because this is very fast. What's the bad scenario? The bad scenario is that our data is backed by a file. So we want to write a program that reads a file. When we do this, and the data has not been brought to the memory, we need to first fetch it from the disk. And once we fetch it from the disk, we also need to search for free space in the physical memory so that we can place the data that we fetch from the disk inside the physical memory and establish the mapping. This is called a major fault. And as you can see in your systems, when you have lots of major faults, it will be much, much, much more expensive. If you have enabled, for example, swap space is something that many of your laptops support right now. If you enable the swap space in your laptops, which can extend basically the physical memory by using part of the disk, then your system will become much slower if it's using part of the swap space and fetches data from the swap space in the physical memory. Okay, we handle the fault. The operating system handles the fault, and then what does it need to do? It needs to store and update the virtual to physical address mapping in the page table, which is stored in the physical memory. So once we find a free physical location for our data, we go to the page table, update the corresponding entry, and we know where our data lies right now. So we establish the virtual to physical mapping. So if a page is not in the physical memory, but it's in the disk, the page table entry will indicate that the virtual page is not in the memory. As we discussed before, the validity bit would be 0. And the access to this page would trigger the page fault exception. The exception you can think of it as an interrupt. So the operating system would figure out that the CPU raised an exception, and it would raise a special program that tries to move data from the disk into the memory. Other processes while this is happening can continue executing, but the process that needs to bring the data from the disk in the memory needs to stop executing. And the OS also can make decisions while this is happening about where to place the data. So before the fault in this scenario, we had these two pages which were stored in the disk. And after the fault was resolved, because we wanted to access this page in our example, the operating system brought this page inside the memory, and it established, as you can see, we had two mappings in the physical memory before. And after the page fault is done, we have 3 mappings inside the free physical memory. How does this happen? So the moment you receive a major page fault, the processor signals a component which we call the I/O controller that starts reading some block from the disk. Because our data is file backed, which means it's stored inside the disk, and we need to start fetching the corresponding block that we requested from the disk. So when the I/O controller figures out that this is the case, it tries to perform a disk-to-memory read. And the disk-to-memory read is happening in modern systems using a direct memory access. So imagine this as some sort of module, the DMA engine, which exists in the systems, that simply has one objective. Transparently from what the core is doing, the core might be executing a program. Transparently, you tell the DMA engine that, okay, start fetching the data from the disk and place it somewhere in the physical memory. The core is not involved at all, and the processor is not involved at all in this process. Does anyone have any idea why we would do it this way? Why we would not simply fetch the data from the disk inside the processor, inside the caches, and then the processor would then store our data in the physical memory? So why do we need the DMA? And don't we just let the processor do the job of fetching from the disk and then writing back to memory? Does anyone any idea? Yes, that's one. That's true, yes.
And maybe because fetching from the disk is a long process, and if we do it on a separate bus, we can push more parallel.
That's one, yes. So what would happen if I would start fetching? That's true, both of your answers are correct. What would happen if I start fetching data from the disk inside the caches? Like what would I cause as a problem? Like how expensive is that? So if I would need to fetch data from the disk inside the cache, inside the processor, the first problem I would cause is I would need to pay a very high price in connectivity. Like I would need to transfer the data over a bus, which is very expensive from the SSD or the SATA drive inside the processor. Second, for every transfer I would do, I would need to evict data from my caches, fetch the corresponding SSD data, the disk data, and then start writing them back to the main memory, which is much slower than simply copying them from the disk directly inside the physical memory. So that's why we're using a DMA engine in modern systems. Once the DMA engine finishes its job and copies the data from the disk to the memory, then the controller signals completion, and the OS can resume the suspended process. And there are many page replacement algorithms which we can use to find out which page are you going to replace inside the physical memory. Modern systems, you can think that they're using some approximation of the least recently used policy, and they're also using the clock algorithm. I will talk about the clock after the break. So let's have a 15-minute break, and we can talk about how the OS replaces pages.
It's not working. You want to throw it?
No, no, I don't. Ah, Opa. Yes.
Yes.
These are this is where I'm very happy if I
I have a question.
Yeah, sure.
I just didn't get it right because what is with the problem if we have the virtual memory, which is bigger than the physical memory? And isn't it possible that we have like two virtual memories and they map to the same physical memory? Or how is
Yes,
this
that's
problem
that's
used?
that's possible. Yeah. So the basic problem is the following, right? If I have a very big, so somehow I need to. There's some data when you write your program, right? That need to be in the disk, and some data which will be in the main memory.
Yes.
So basically, I need to find a way that when you write your program, I will transparently do this for you. So you don't need to care about where you place your data in the physical memory. This is the more important, let's say, functionality of virtual memory. The fact that I abstract this from the programmer does not need to know about it. So I automatically manage basically how data will be placed in the physical memory or in the disk without you caring about it.
Okay.
This is the most fundamental part rather than the infinite memory part. The infinite memory, you can remove it from it. Like, it's not very important. This is how people perceive this in the older days.
Okay.
But the most important is that I automatically manage where your data will be placed without you caring about it.
Okay. So this is the main problem and not that
The infinite memory is not a thing, right?
Okay, yeah, it makes sense.
Yeah, I agree. I don't like in general this, but this is how people teach it usually. And I didn't want to, innovate a lot. But I wouldn't focus on the part that memory is infinite. That's not important.
Okay, that's what kind of
Yeah, the
confused me
important
because
part is that you have a very large virtual address space. That's fine. And no matter what you do there, I will transparently and without the programmer caring handle the allocation of data either in the disk or in the physical memory.
Okay, and the page table, it's like that you have encoded your virtual address in like the normal address, right?
Yeah.
Or
So
you-
the page table is a very simple. It's like a dictionary. I know the name of the person. I need to find where they live. They live. So I give the virtual address, and based on the virtual address, I get the location that they live. Whether they live in the disk or in the memory is my responsibility. It's not the programmer's responsibility.
And on the multi-level page table, we are like iterating over the 4 page tables, right?
Yes.
And then if you are writing a memory, do we start in the first one or do we iterate to the last one and then start and come like?
So imagine this as the following. So the first page table describes a very large location of where your data might be at.
Okay.
The second level of the page table describes a bit smaller location where your data might be at. The third a bit smaller,
okay.
and the last one, the 4 kilobyte location. So if your program, let's say, uses 1 gigabyte of data, probably what will happen is the following. You use only one entry for the first page table. You would use only one entry for the second, only one entry for the third, and many entries for the last. Okay. This means that for the intermediate ones, you would not need to store extra entries for the page table. You would need to store one for this specific process. Okay. Which reduces the total size of the page table. Okay. If you want to learn more about it, there is a concept which I don't want to dive deeper here. It's called the radix tree. Okay. The radix tree imagines as a prefix tree. Prefix tree means that the root of my tree, like when I want to describe names, right? And let's say I want to describe names like a name is Muhammad. Okay. The way I would look this up is I would encode it as MO, and then after MO there are multiple names that come right. MO Muhammad, MO Ali, or something like that. Yeah. So you can think of it as encoding, as searching for a smaller part of the virtual address at the beginning. Okay. Then I search for a bigger part of the virtual address, a bigger part of the virtual address, until I have the whole virtual address and find the final one. Okay, yeah, that makes a lot of sense. Yeah. Thank you very much. Hi, quick question. What was LRU? It's the least recently used, which means that I want to select a page which the least recently used, I did not use it at all in the last, let's say, time window. It's used a lot in caches, in many replacement points. When we want to figure out which data to replace inside the physical memory, where the system right now is using some approximation of this, of the least recently used points. So let's continue where we left it. So we fetch our data from the disk. We want to place it inside the physical memory. And right now we figure out that the physical memory is full. So we do not know where to place our data. And we need to make room for the data. Is it fine? Okay. And we need to make room for the data that we need to place inside the physical memory. And we need to make a decision. Which data to evict from the physical memory, remove it from the physical memory, and place it back in the disk. So modern systems use an approximation of the least recently used policy. We try to evict the data that has been the least recently used ones. But one of these approximations is called the clock algorithm, which I'm going to discuss quickly. So the clock algorithm works in the following way. So we keep a circular list of the physical frames in the memory. So as you can see, for each physical frame, we keep 1 bit. So for each page in the physical memory, we keep 1 bit. And what we do is the following. We keep a pointer to the last examined frame in the list. So for example, we wanted to evict this one, right? Or our pointer points to this one. And we figure out that we access this one, or we access this physical page. And when we access this physical page, we set the bit to R. R means that it has been recently accessed. And we encode this information as a bit. If it has been recently accessed, the bit will be 1 in the physical page. So when we want to replace a frame, the first thing we do is that we start the clock. The clock starts and goes rightwise. And whenever we meet a bit, whenever we see a bit, a physical frame, where the bit is set to 0, this means that it's not recently used. That's our assumption, right? So as we move the clock, all the set bits will become 0, which means that we set their property, we reset the property, we assume they have not been recently used because the clock went by them. And the moment we see a physical frame which has not been used, which means that the bit is 0, then we select this bit as the eviction candidate. And what we do is that we also set the hand pointer to the next frame in the list. So once we evict something, we move the hand pointer to the next one. Can someone tell me which property this algorithm is missing fundamentally and would not work well in the systems? Like if I just use 1 bit to figure out whether my data is recently or not recently used, what am I missing out basically? Like how would I figure out if my data have been very important to be kept in the physical memory in the history of like my program running? This would be impossible to store using this algorithm because it cannot capture information about the history and how many times I have accessed this page in the memory. It would only capture a partial history, very recent history of what happened with the page in the main memory. That's why modern systems use a lot more intelligent and sophisticated algorithms to do the page replacement. So you can think of the analogous problem when it comes to caches. So the physical memory, you can think it as a cache for the disk. So we have it's managed by the system software via the virtual memory subsystem, and the page replacement is similar to the cache replacement. So the page table is a tag store, and the difference is that, what is the key difference is that the speed of access to the cache in the physical memory is different. We can access the cache in 1, 2, 3, 4 nanoseconds. We can access the main memory in 100 nanoseconds. Second, the number of blocks. The cache has, let's say, the L1 cache has a 32, 64 kilobyte size, which means it has a lot less blocks compared to the physical memory, which stores, let's say, 2, 4, 16 gigabytes of data. We also have a tolerable amount of time to find the replacement candidate. Fetching the data from the disk can happen in microseconds. Fetching data from the cache can happen in nanoseconds. So we don't have the same slack in the same time to make the eviction decision in these two scenarios. If I fetch my data from the disk and it takes, let's say, 1, 2 microseconds, then I have time to make an intelligent decision of which data I would evict from my physical memory. The second and biggest property that virtual memory has been used in the last 20, 30 years is memory protection. So we have multiple programs and processes which run concurrently, right? And each process has its own page table. Each process also can use its entire virtual address space without worrying about where other programs are, because the page table would isolate fundamentally these two processes by storing different physical locations from the data of two different processes. So a process can only access the physical pages mapped in its page table. It cannot, for example, overwrite the memory locations or the memory of another process because it does not have access to the page table of another process. This provides protection and isolation between processes and enables access controls mechanisms per page. So we could figure out given a page table, we can figure out whether we have permissions over a specific page. In this example, we have two different virtual address spaces. Each one of the processes using two virtual pages, and you can figure out the following information here. VP1 and VP2, VP1 maps to PP2, VP2 maps to PP7, VP1 maps to PP7. What does that mean? That we have two processes whose virtual pages map to the same physical page. For example, I ran two processes that use TensorFlow. They both use the same library, which is TensorFlow, and they map to the same code, to the same physical page that contain the code. We need to enforce some sort of permissions and priorities when it comes to this specific physical page, because we do not want one application to go and change the code of TensorFlow. So we need to make and register this specific physical page as a read-only library code. If the virtual address space for process 2 is malicious and wants to hack the system, it cannot go and basically change right now PP7 and change the contents of TensorFlow or any library so that it can hack the virtual address space of process 1. So the access and the protection control happens via virtual memory. So virtual memory does not only map virtual addresses to physical addresses, it also keeps track of the protection mechanisms for each virtual page. So we have page level access control. So not every process is allowed to access every page. So we need some sort of kernel level support to access the system pages. We may not be able to execute instructions in some pages. For example, we might avoid attacks like Stack Overflow, if you know about it, where we overflow the stack with some instructions and the attacker executes these instructions. If we would somehow not enable the attacker to execute specific pages, execute code from the specific pages, then we would avoid such attacks. And the idea is to store the access control information on a page basis in the processes page table. So we want to enforce the access control at the same time as translation. The moment we find out the location of our data inside the physical memory, that's the moment we will figure out whether we have permissions to access this page in the physical memory. You can see this example again. We extend basically the page table entries with permission bits, and we check bits on each access and during a page fault. And if we violate these permissions, then we generate an exception. For example, in process I, we have VP0, which we can read. So we can read from this virtual page. We can only read data, but we cannot write data. So in PP6, in this page, we can only read from it, and we cannot write to it. Why is this the case? Because process J is the only one who can read and write to it. So we do not want process I to write to it and create a synchronization problem, for example, of who writes and when. There are multiple privilege levels in x86 which we encode using the access protection bits. I'm not going to go deep into this. The two most important ones is level 3 and level 0. Either the operating system can do stuff or the user space can do stuff, our programs. And if we take a closer look at the page directory entry and the page table entry, this is in 32-bit systems where we have a two-level page table. We have the PDE, which is the first level, and the PTE, which is the second level. We can see that using the first level, we can encode permissions for a larger number of memory pages. Using the last level, we can encode permissions for a smaller number of pages. What does this give as a possibility? Using a single entry in the first level of the page table, we can cover up the permissions for a larger number of pages. For example, using the first level of the page table in 32-bit systems and using the access control bits there, we can encode the protection bits for 1024 pages in the page table, and we don't need to do it for every 4 kilobyte page. However, the last level of the page table, which contains a translation from the 4 kilobyte virtual page to the 4 kilobyte physical page, it can protect only one page at a time because each entry protects one entry. And as you can see, we can combine basically these two so that we can encode so that we can create more complicated schemes when it comes to protection. We can encode some pages, we can protect at the 1 megabyte granularity, let's say. Some other pages, we can protect them at the 4 kilobyte granularity. And this way, you can have a multi-granular support for access protection. So the question is right now the following. Let's say that somehow your hardware is unreliable, and someone can flip the access protection bits. So some hacker tried to hack in the system, and their job is to basically perturb the access protection bits. And they do this so that the user level program, so you're at the user level, you can gain supervisor level access. Basically, you can be the kernel. And the way you do this is you try to flip the access control bits from the user to the supervisor, which means that this virtual page does not belong anymore to the user space program. It belongs to the operating system, which is a much more privileged process. The question is, can this happen? Does anyone know a way that this can happen? That I can flip bits inside the memory? Correct. Yes, RowHammer. I'm not sure if you have heard in the course about RowHammer, but if you remember RowHammer, it's a technique with which we can predictably induce errors in most DRAM memory chips. So we can predictably induce bit flips in commodity DRAM chips. And this is a first example how a simple hardware failure mechanism can create a widespread system security vulnerability. And this has been published in 2014 by a paper from our group. And we saw how RowHammer works. So we open up a row. We activate a row in DRAM. And then we close the row. We open up again the row. We close it again. And what do we find out? We found out that there are some bit flips in the neighboring rows. So by hammering a single row, activating and reactivating and reactivating and accessing again and again and again a single row in the system, we can cause bit flips and perturbations in the neighboring rows. These are called the victim rows, which suffer from this problem after accessing the hammered row. So if we repeatedly read the row enough times, we can induce errors which are called disturbance errors because they are caused by electrical disturbance. And these errors can be induced in most of the real DRAM chips you can buy today and the ones that are in your system. How does this work? We can have a simple program that induces many errors. How? By we try to avoid cache hits. We try to bypass the caches and access the memory and the memory only. So we flush the cache line from the cache line X, and we try to avoid row hits to X. To avoid row hits to 1 and have two different rows which we activate, X and Y, we basically do the following. We access row X, then we access row Y, which activates two different rows, neighboring rows, and then we flush the contents of X and Y from the caches. So next time we access X and Y, they will not be in the caches. We will again go to the main memory and do the same thing. What would happen in this scenario? The rows in between X and Y would be the victim rows because they would be encapsulated by X and Y, and they would receive some electrical charge magically that changes their bits. And you can see that we observed many errors in real systems. This is a real reliability and security issue, and one can take over an otherwise secure system with this approach. And this has been shown by Project Zero, where they tried to exploit the DRAM RowHammer bug to gain privileged access. So the Google's original RowHammer attack paper shows the following kernel exploit. So the x86 page table entries are dense and trusted. So as we discussed before, they control the access to the physical memory, and a bit in the PTEs, in the page table entries, physical page number, can give a process the access to a different physical page. So the aim of the exploit is to get access to the page table and give access to all of physical memory. So if we would basically flip some bits in the page table, we could simply fake the system, assuming we are the hypervisor, we are the kernel. And we wanted to in this paper, they wanted to maximize the chances that the bit flip is useful. And they did this by spraying the physical memory with page tables. Let me explain how this was done. This is the virtual address space, and this is the physical memory. So the first thing they did was they simply used a mapping. They established a mapping between this virtual page and this virtual page. And this mapping was established using the page table. But they started creating more virtual pages that would map to the same file. So basically, they created, from multiple different processes, they created different page table entries that would all point to exactly the same file. So we would have multiple processes in the system, multiple page tables, and the page tables would all point to this specific file. And what they achieved is that they basically fed up the whole memory with page table entries that would point to the same file. So what was the assumption that they have? If a bit in the right place in the PT flips, then the corresponding virtual address now points to a wrong physical page with read-write access. So if they somehow could flip a bit inside this page table, then they could get access to the whole system. And the chances are this wrong page contains a page table itself. So if you figure out a way to flip bits, then there is a high chance that you will basically point to the page table. An attacker can also read and write page tables this way. Basically, you fill up the whole memory with page tables, you do your RowHammer, and then what you achieve is that you start perturbing the bits of the page table to make sure you point to the locations that you want. We're not going to how they exploited this, but that's the premise of the attack. And let's see right now some more issues in virtual memory. So this was a very good example of how people combine one reliability problem and one existing abstraction in the system, which is virtual memory, to take over the whole system. So there are three major issues in virtual memory. First is how large is the page table and how do we store it? How do we access it? Second, how can we speed up the translation process and the access control check? And third, when do we do the translation in relation to the cache access? And there are many more issues which we will not cover in detail. How large is the page table? We basically answered this, and the idea was multi-level page tables. And in modern systems, recall that we're using multi-level page tables. They do not use just a single level. Each one of these levels is used to store pointers for the next level. And if the pointers are not valid, we do not need to store the next level, basically. So how do we access the page table? With a page table-based register. And if the VPN is out of bounds, then the process did not allocate the virtual page, which is an access control exception. If you see segmentation faults, that's why they happen, because you try to access a virtual page that was not there in your page table. And the OS figured out that you don't have access to this page. So this is how x86 systems, again, use small pages. I will not go into details with respect to this. And I will jump to the second issue directly because we discussed about the page table. So the big question is how can we speed up translation and access control check? And this is one of the main research directions that the community has been focusing on for more than the last 30 years. How fast is the address translation? How can we make it fast? So modern systems use a hardware structure that caches the page table entries and reduces the number of memory accesses to look up the page table. Let me remind you the following. If we would do one additional memory access per memory access, then we would have high performance degradation. So researchers have introduced a component that can basically store and give us very quickly the virtual to physical translation using the page table entry without requiring going to the main memory every time we want to read the page table. So how does the translation happen? The translation happens this way in modern systems. We have a core, and the core ships the virtual address. It sends the virtual address to a component which we call the memory management unit. So you can think this component as part of the core, somewhere near the core. It's a hardware component and is responsible for translating your addresses, the virtual address to the physical address. How does it do this? It tries to read the page table and store the most recently or some page table entries so that you do not need to go to the memory hierarchy every time you request a virtual to physical address translation and you retrieve it quickly from the memory management unit. So the memory management unit is responsible for resolving the others' translation requests. We have one of these per core. If your system has a 6-ARM core, let's say, you have 6 memory management units, one for each core. And it typically has 3 key components. The most important component is the translation look-aside buffer. The translation look-aside buffer caches recently used virtual to physical translations. In other words, it caches the most recently used page table entries that contain the virtual to physical translation. Second, it uses page table caches. As you recall, we have multiple levels in the page table, and each level acts as a pointer to the next level. So the page table caches offer very fast access to the intermediate levels of a multi-level page table. We give it a pointer, and it gives us the pointer to the next level. There's also a hardware page table walker that sequentially accesses the different levels of the page table to fetch the required page table entry. So imagine it as a circuitry fixed in hardware that is able to go and traverse the page table for us instead of doing it at the software level. This is an example memory management unit in Intel Skylake processors where we have 2 TLBs at the first level, 2 L1 TLBs, one that stores translations for instructions, one that stores translations for data, one L2 TLB much larger, which stores translations for both instructions and data. And then if we miss in this TLB, then we need to perform the walk, basically. If we do not find the virtual to physical translation inside any of the hardware structures which store the most recently ones, which is the TLBs, then we need to somehow go to the page table in memory to figure out where is the data inside, where does the data reside in the physical memory. So the idea is to cast the page table entries in a hardware structure in the processor to speed up translation. This is the translation look-aside buffer. It's a very small cache which stores the recently used page table entries, and it reduces the number of memory access required for most instruction fetches and load stores to only 1 TLB access. In most systems, based on my experience at least, 95% of the memory accesses you do, or even more, are filtered by the TLB. You do not need to go to the main memory to fetch the page table to find the location of your data in the physical memory. How does that work? It's a similar concept to caches. We have the concept of indices, tags, data, and status. So we take the virtual page number, we use it, we form the index, we go to the corresponding set in the TLB, and we find out if the tags match, and if the tags match, then we figure out that the translation is there. And if the translation is there, we form the physical address. But the TLB is small, and it cannot hold all the potential page table entries. So some translation requests will inevitably miss in the TLB. We cannot find everything in the TLB. So we must access the memory at some point to find the required page table entry. So this process at the hardware level is called watching the page table. It has a large performance penalty I will discuss later. And we have better TLB management and prefetching, which can reduce the TLB misses. And the question is, who handles the TLB misses, hardware or software? So this is a question that has been answered, and we do it in a hardware-based manner in modern systems. But in older systems, we're not doing it this way. So our first approach is hardware managed. So whenever we miss in the L2 TLB, we trigger a circuitry that simply does the pointer chasing of the page table for us. It's looking up the page table for us. Once this is completed, we fetch the page table entry and insert it inside the TLB. So if the TLB is full, again, we have the same principles. We need to evict an entry and place our page table entry there. This is done transparently to system software. So you walk the page table completely in hardware. The programmer doesn't need to know any of these. The approach number 2 is a software-managed approach, which was done in MIPS processors. Whenever we have an L2 TLB miss, we would raise an exception. The program raises an exception, the processor stops. The operating system takes over and starts watching the page table, accessing the page table to figure out what is the virtual to physical mapping. So the operating system fetches the page table entry and controls how you will insert it or not in the TLB subsystem. The good part with the hardware managed TLB is that you don't need exceptions on a TLB miss. Exceptions are very expensive. Handling the control over to the operating system is a very expensive process. Second, you might have independent instructions which can execute at the same time. If the operating system would take over, then you cannot execute any other instructions from the same program. And third, you do not need to bring any extra instructions or data into the caches to fetch, for example, the operating system code or the operating system data that they will handle the exception. However, the page table organization in this scenario is fixed. There is no flexibility with respect to the design of the page table. Once we fix the hardware to access this type of page table with 4 levels, we cannot go and change this from the operating system side. The operating system needs to use a 4-level page table. If it uses a 2-level page table, the system will break because hardware expects that the page table is a 4-level page table. The second approach is a software managed TLB, where the OS can define the page table organization. We have more sophisticated TLB replacement policies, but we need to generate an exception. So we have a performance overhead because every time we have an L2 TLB miss, then to find the translation, we would need to raise an exception, fetch the code of the operating system, flush the whole pipeline so that we can fetch the data and execution and instructions of the operating system. Then the operating system would walk the page table. Okay, we have more flexibility, can do whatever it wants, but we would basically degrade performance of applications which have lots of L2 TLB misses and cannot sustain the throughput and the size of the L2 TLB for translations. When it comes to the L1 TLB, data TLB, modern systems use 3 different page sizes: 4 kilobytes, 2 megabytes, and 1 gigabyte page sizes. I will not go into deeper details of how this is done, but imagine it as we do not know the page size a priori. We know it only after we perform the address translation. So we have virtual to physical mappings inserted in the corresponding TLB after a TLB miss, and during a translation request, all the 3 TLBs are looked up in parallel. So this is a complicated process, which I don't have very much time to explain, but we have 3 TLBs, one that stores translations for 4 kilobyte pages, one that stores translations for 2 megabyte pages, and one that stores translations for 1 gigabyte pages. So right now, the modern Linux and the operating systems do not just use 1 page size, they use 3 page sizes, usually. And we need to figure out, given the virtual address, what is our page size? And the TLB, these 3 TLBs, if we have a hit in the L1 1 gigabyte, then we would know that our page size is 1 gigabyte. If we would hit in the L1 2 megabyte, then we would know that the page size is 2 megabytes. And if we would hit in the L1 4 kilobyte, then we would realize that our page size is 4 kilobytes. That's why we do 3 parallel memory accesses to figure out to which TLB are we hitting, so that we can quickly find which is our page size. Second, we have the L2 unified TLB. The L2 unified TLB caches translations for both instructions and data. Again, it's private per individual core. And we have 2 separate L2 TLB structures for 4 kilobyte, 2 megabyte pages and 1 gigabyte pages. The question is, how can the L2 TLB support both 4 kilobyte and 2 megabyte page sizes using a single structure? There is not publicly enough information, so I'm going to skip this part so that we make it more simple. But the most important part is what happens if we miss in the L2 TLB. And if we miss in the L2 TLB, we have a hardware page table walker. So you can imagine this as a per core hardware component that walks the multi-level page table to avoid the expensive context switches. So you can think of it same to the things you do in the lab. You can think of it as an FSM, basically, that goes and reads a pointer in every cycle. And once it figures out that it loaded not a pointer, but the actual page table entry, then it will stop, the FSM will stop and resolve its execution. So the hardware page table walker consists of 2 components: the state machine, the FSM, that is designed to be aware of the architecture's page table structure. It needs to do 4 accesses, and registers that keep track of outstanding TLB misses, because we might want to perform more than 1 TLB miss, handle more than 1 TLB miss at the same time. What is the good part? We avoid the need for context switch on TLB misses. We overlap the TLB misses with useful computation, and we can support concurrent TLB misses. The disadvantages, we have hardware area and power overheads because we have a new hardware that accesses the page table. You have a new FSM. We have limited flexibility compared to software page table walk, which is what we discussed before. And here you can see an example of why doing this in hardware compared to software is very important. Let's say we had a software page table walker. So we would load A, which corresponds to VPN equals 1. And we have a TLB miss. We have an L2 TLB miss. So after the L2 TLB miss, we would have a context switch. And the context switch would give the control to the operating system, which would be responsible for running the TLB miss handler and giving us back the translation. After the TLB miss is handled and the OS gives the control back to the hardware, then we would perform the load for address B, which is VPN equals 5. And in this scenario, it would be a TLB hit. Everything nice. In the case of the hardware page table walker, though, we would again load A, which would be a TLB miss, but in this scenario, we do not context switch to the operating system. At the same time, because we do not context switch, we can perform the load A in a pipeline manner. So in a pipeline manner, we perform the load A with VPN equals 5. And at the same time, we have a TLB hit for load B. And we have the page table walk in the hardware level that services the TLB miss for load A. So what did we gain? We saved these cycles. And we saved these cycles because in this scenario, we first overlapped the load B access and the translation process with the load A. And we also save time because we do not spend time in context switching and giving control to the operating system. Any questions? Okay. Then there's a component that the page table walker is using, which is called the page walk caches. And the page walk caches cache translations from non-leaf levels of the multi-level page table to accelerate page table walks. So we have these intermediate levels which store pointers in the page table. And you can imagine the page walk caches as very fast components that basically avoid these intermediate levels of the page table. So there are more issues when it comes to address translation, which is with respect to caching. I don't want to go there because this is a more advanced concept. And I'm going to talk more about the evolution of the virtual memory system. So as you can see on the left, back in the days, not so far basically back, but back in the day. So we did not have a very advanced address translation subsystem. We had simply an L1 data TLB, an L1 instruction TLB. And then when we missed, we had a software page table walker. We would raise an exception. We would go back to the OS. And this happened because of the following reason, that as I discussed before, there was no concept of data-centric, data-aware. We were not using lots of data, basically. We did not design our systems based on the size of the data. Right now, we have a lot more components in the address translation subsystem. Why? Because there are many, many workloads which make use of a large data footprint, and we need to cover it up with more TLBs. We need to cover it up with a page table walker. We do not need to context switch every time we're missing the TLBs. As you can see, these are two systems, the A14 processor from Apple, which is in the iPhone 12 Pro. And this is the Intel AMD and ARM architectures. And as you can see, there are fundamentally different properties in these two. For example, the A14 is using an L2 TLB with 3 kilo entries, while in most Intel AMD and ARM processors, you can find L2 TLBs with up to, let's say, 2 kilo entries. And as you can see, the page sizes are also different. Apple is using a 16 kilobyte page size, base page size, while Intel and AMD and ARM are using a 4 kilobyte page size. And now let's talk about the virtual memory overhead, which is also the main part of my research endeavors. So we recently published a work called Virtuoso, which enables how to enable fast and accurate virtual memory research with an imitation-based operating system simulation methodology. I'm not going to go deeper into how we did this and how the simulator is formed, but I put this here so that I can show you the concept of virtual memory overheads. So we have modern systems that use GPUs, CPUs, network interface cards that all use virtual memory these days. So virtual memory is a cornerstone of most modern computing systems. And the question is, does virtual memory come for free? No, virtual memory causes high performance overheads because of two reasons. Number one, memory allocation, and number two, address translation. So let's see first the memory allocation overheads. So we have emerging workloads, as you may have heard, function as a service workload, serverless computing. We have LLMs, we have short input, short output LLM inference models, which are short running. They run in less than a second. When you execute your query in ChatGPT, it runs in less than okay, it doesn't, but close to less than a second. It also has a very high spawning throughput. We want to execute as many queries as possible at the same time, because the whole universe is using ChatGPT or Gemini these days. What's the problem with this? These applications are spending a lot of time on OS memory allocation routines. You basically try to allocate, let's say, the KV cache or some data structures in your LLMs or in your functions, which takes time. And the time it takes to allocate in the operating system all this data is often more than the execution time of the workload itself, because the workload might run on a GPU or an accelerator, while your OS memory allocation would run on the CPU. So we have time spent in the operating system which cannot be amortized due to the short execution of the workload. In this plot, we demonstrate the fraction of the total execution time as a percentage of the physical memory allocation. How much time do you spend in physical memory allocation compared to the total execution time across some workloads? And as you can see here, you can see Llama, Bagel, and Mistral, which are famous LLM inference workloads. And as you can see, we have an average of 32% of the total execution time spent on simply allocating memory. We didn't run anything with respect to our program. We simply allocated memory. And the second type of overhead is the address translation overhead. We have another set of workloads like sparse machine learning. We have graph neural networks. We have bioinformatics workloads, which has vast data footprints. We have graph analytics. We have databases that are long running. For example, we run our bioinformatics workload. It runs for 1-2 days. And they also have irregular memory access because of the properties of their inputs. These workloads cannot fit basically all this data and the translations inside the TLB. So we have lots of TLB misses. We have lots of page table walks, which means we have a high latency address translation. And this high latency address translation basically stops us from fetching data quickly. Basically, in this plot, we demonstrate that address translation on average takes 26% of the total execution time in these very demanding irregular workloads. So we have, in a nutshell, two types of overheads, which are caused in diverse emerging workloads. We have both address translation and minor page faults, which basically is the memory allocation in these workloads. And the virtual memory overheads are expected to increase as we transition to much larger physical address spaces. So as we go into the future, we have, for example, in modern systems, we have CPU and GPU together working, and they use a single memory, which we call the unified memories, virtual memory scenario. We have direct storage access. If you have seen devices where we can directly access the storage without using a memory. We also have memory disaggregation. Right now, from your computer, there are systems which enable you to use not only the DRAM available in your laptops, but also the DRAM available in a remote node somewhere else, which increases your effective memory capacity, basically. We integrated this simulator with 5 different simulators, and we built tools that have many state-of-the-art techniques, and we validated against high-end server-grade CPUs, and we demonstrate many use cases. If anyone is interested, we can discuss and see how you can have your first research opportunity. And you can find it online and play with it. I have the documentation as well, so you can get started. And in general, I have been focusing a lot in the group in general on how to improve the virtual memory overheads. Here is a work we published in Micro 2023, 2 years ago, on how we can leverage the caches to store page table entries and not just store them in the TLB subsystem, but store them also by repurposing the data caches in the system. We also published another work where we show that placing a virtual page anywhere in the physical memory is not very helpful, and it would be good if we establish a more restrictive mapping so that we can do address translation faster. And this is a bigger work where we show that we need to completely rethink the virtual memory subsystem in order to alleviate its overheads. In summary, virtual memory gives the illusion of infinite capacity. We have a subset of virtual pages which are located in physical memory, and a page table maps the virtual pages to the physical pages. It acts as a dictionary, and this process is called address translation. So we have a TLB and a memory management unit that tries to speed up this address translation inside the core. We have the multi-level page tables which try to reduce the size of the page table. And if we try to use different page tables for different programs, we can provide memory protection without the programmers needing to synchronize over the memory access they're doing. There is a lot more in virtual memory which we will not cover. When it comes to virtual machines running programs and hypervisors, you can think of concepts like virtualized environments where we don't have simply one operating system. We have two. We have the guest operating systems and the host operating systems. So we do not need to translate just from host virtual to host physical. We need to translate from guest virtual, from the guest operating system, to host virtual, to the host operating system, and then from host virtual to host physical, which makes the address translation process both a lot more complicated and a lot more expensive. So you have seen, and you may have understood, that virtual memory is one of the most successful examples of architectural support for programmers. It's one of the first endeavors of research where people try to provide a much better abstraction to the programmer to make their life easier. And it's one, I think, of the one of the few, basically, hardware OS co-design primitives that have been actually established in the processor nowadays. So going forward, there are many more problems with respect to how virtual memory would scale. Like if we have very large physical memory sizes, I described this before with SSDs, with unified virtual memory between GPU and CPU. We have hybrid physical memory systems. We might have a DRAM, a non-volatile memory. We might have an SSD as well. We might have many accelerators in the system. We can have neural processing units, CPUs, GPUs working together and accessing the same physical memory. And we might have virtualized environments like hypervisors, microkernels, and other weird software structures. You can find our lectures on YouTube, more lectures on virtual memory. This is an old lecture from CMU, from Onur. And you can also find the cutting-edge research discussions we did for these three works in our computer architecture course in the master's level. And thanks a lot for your attention. And I'm happy to answer any questions you have.
Το μάτσι είναι σε μία ώρα. Είναι μαλάκας. Τραγικό μου. Όταν μένει ζηρή.